Good evening. Welcome to the NCCR Automation Seminar Series. So this, as you also saw in the invitation, this is going to be the last seminar from the first series of the NCCR Automation Seminar Series. So we have the pleasure of hosting Professor Sebastian Trimpe and Professor Marco Zimmerling today. So they kindly accepted to give a presentation today, and we're really looking forward to your talk, to your joint talk. Before that, I would be happy to give a short introduction of the speakers today, and then I will leave the stage for first Marco and then Sebastian. I think they will interchange the presentation, yeah. So I will start with Marco, who will start the presentation. So Marco Zimmerling will be very soon a full professor at the University of Freiburg in Germany, where he will be the head of the Network Embedded Systems Lab. Currently, he is an independent group leader at TU Dresden in Germany. He received his PhD in computer engineering from ETH Zurich in 2015 and a diploma in computer science in 2009 from TU Dresden. His research actually is around embedded systems and wireless networking with the goal of designing dependable and sustainable network systems. He has received multiple awards, notably 2015 ACM SIGBET Dissertation Award, EDAA Outstanding Dissertation Award in 2016, Best Paper Awards at ACM IEEE ICCPS in 2019, and ACM Census 2013, and some more. Our second speaker, Professor Sebastian Trimpe, is a full professor at the Mechanical Engineering Department at RWTH Aachen University, and he's the head of the newly established Institute for Data Science, from where I believe it's initiated from 2020, where the research is focused on intersections of control, machine learning, networks, and robotics. Before moving to Aachen, Sebastian was a group leader at Max Planck Institute for Intelligent Systems. He received his PhD again from ETH Zurich in 2013 at the Institute for Dynamic Systems and Control. He received multiple awards, notably again Triennial IFAC World Congress Interactive Paper Prize, Klaus Schirra Award for achievements in public understanding of science, Best Paper Award at International Conference on Cyber Physical Systems, and many more. Again, I thank you very much for joining us today, and we're very much looking forward for your talk. So stage is yours, Marco.
Yeah, so thanks a lot for the introduction and the very kind invitation. It's a pleasure to give a talk at the seminar series together with Sebastian. So this is joint work together with our PhD students, Fabian, Dominic, and Alexander, as well as with Roman Jakob and Lothar Thiele from ETH Zurich. So the fundamental research question that motivated most of our work, I would say, is whether it's possible to do fast and reliable feedback control over multi-hop wireless networks. And this is an important question because this feature is essential for many existing and envisioned cyber-physical systems across many domains. Think about smart production, intelligent transportation, or process control. Catering for the service, however, is challenging because it requires fast and reliable data exchange across large distances between different entities. And these entities may actually be mobile in many of these applications, and also the environment around these entities is highly dynamic, which leads to highly dynamic networks. Some of the entities may be very limited in their resources. Think about sensors that are powered by batteries or actually harvesting energy from the environment. So we have entities that are limited in their compute power, memory, or energy resources. Nevertheless, we need to provide guarantees in order for cyber-physical systems to be used in critical application scenarios, despite all these challenges. So there appears to be a fundamental conflict between properties of wireless networks and the requirements of feedback control. These networks, as we just said, are highly dynamic, and they only provide sparse and imperfect information transfer. We, for example, cannot avoid packet losses in these systems. On the other hand, feedback control requires reliable information exchange, and this also needs to be very quick when you want to control and coordinate fast physical systems, for example, mechanical systems in certain applications. In the first part of this talk, we will illustrate how we attacked the challenge of providing guarantees across these unreliable and highly dynamic infrastructures or networks. And the second part focuses on saving resources, addressing the limited resources in these systems. When we started out to work on this project a couple of years ago, we looked at the existing literature and systems and categorized them along two basic dimensions. One of them is the process dynamics, whether the existing literature looked at controlling fast physical systems or slow physical systems. So it's a very rough classification here, but fast we could sort of imagine that these are dynamics of tens to a few hundreds of milliseconds. And the second dimension is the network diameter, so the extent of these wireless networks. In the simplest case, this is a single hop network where every entity or agent can directly talk to every other agent. Or in larger systems, a large production site, a large tunnel, as we will see shortly, communication needs to occur across multiple hops to reach all entities in the system. In the simplest case, we have a very small network and want to control a slow physical system, for example, a double tank process. And this was demonstrated, for example, by the group of Kalle Johansson and KTH in 2013. And they used low-cost, low-power Zigbee devices to control these water tank systems using update intervals of 1 to 10 seconds. People also looked at wireless control across larger networks, multi-hop networks. For example, you need this when you want to control the light intensity in a tunnel. These tunnels can be very long, as you know very well in Switzerland, I guess. But of course, these systems or these processes are rather slow. So here in this work from a group in Italy, they used update intervals of tens of seconds. So this is one example of slow wireless control across a larger multi-hop network. And some groups have also looked at single hop networks or controlling fast physical systems across single hop networks, for example, to stabilize a pendulum using such a small network as shown here in the figure, just 2-3 devices on a desk in order to stabilize an inverted pendulum, where of course we need faster update intervals, a few to tens of milliseconds. But this was only limited to very small networks. But looking at this upper right-hand corner here, we had to conclude that there's no existing solution, whereas this design point is critical for certain classes of cyber-physical systems. And this sort of drove most of our research over the past years to find a solution in this upper right-hand corner. And the key challenges sort of to address this design point were that when we want to connect sensors, controllers, and actuators, we have to exchange messages across these large-scale dynamic wireless networks. And this, of course, takes time. So messages need to travel through the network to the controllers, possibly back to the actuators when they're not co-located. And due to blocking objects or packet losses, packets need to be retransmitted. This takes varying amounts of time, leading to significant end-to-end jitter in these systems. And of course, packet losses are unavoidable. And very often these packet losses are also correlated because we have certain interference, for example, that affects the network in a certain area across a certain amount of time, and therefore leads to multiple consecutive packet losses, which then become highly correlated. And our basic approach to address these challenges has been a co-design of the wireless embedded system and the controllers. Specifically, we were trying to sort of mitigate these challenges, reduce the delays, for example, mitigate the jitter and the packet losses by designing the software and hardware components that make up this wireless network. And then based on the resulting key properties of the network, design our controllers and perform an end-to-end analysis of the system. So first design the embedded hardware components, then design the controllers with respect to the resulting properties. So let's dive a little bit deeper into the network components. And one of the first questions is, what kind of architecture or hardware platform did we use? So how do these devices look like that communicate with each other? And we opted for a predictable architecture where we sort of allocated sensing, actuation, and control, the application tasks, to one processor, and the wireless communication tasks, specifically executing the wireless communication protocol, to another dedicated communication processor. This, of course, allows these two types of tasks to execute in parallel, which is good for efficiency. And by designing the interconnect that allows these two processes to exchange messages in a certain way, where we could essentially guarantee that one processor never influences the other processor. So essentially avoiding interference between communication and control, which is sort of a modular design that also allowed us to sort of develop and design things.
Some are negative, some are positive.
Sorry. Yeah. Okay, so we have a certain architecture here that is predictable and allows these processes to communicate, exchange messages with formally verified execution times. Now that we know how the devices look like, let's look at how they communicate. How do they exchange messages with each other? And this should be also highly predictable in terms of delay. End-to-end delays needs to be very fast, highly reliable, even though these networks are highly dynamic. And a communication scheme that we developed back in 2011 provides these properties. And I'm going to illustrate briefly how this communication scheme works. So let's imagine we have one agent in the system that has a message. It wants to share, for example, its state with all other agents in the system. And the agent will transmit the message. It needs to transmit it in order to share it. And this is illustrated in blue here. And its two neighbors in red are going to receive the message at about the same time. And this communication scheme ensures that these two red nodes that just received the message are also going to transmit the message at the same time. Now you may wonder, okay, how can this work? Because these two devices are transmitting the same message at the same time. So this is going to lead to a packet collision, which, as you may know from your networking course, will lead to packet loss. But due to certain physical layer effects, this doesn't happen. So with very high probability, these red nodes illustrated here in the figure are still able to receive the packet successfully with a certain very high probability. And the communication scheme continues like this. So nodes keep transmitting concurrently, other nodes receive, and then again transmit concurrently. The key message here is, in order to run this protocol, the devices don't need to understand anything about the network. They don't need to understand how many nodes there are, what are the distances, what are the conditions of the wireless channel. They only need to wait for a packet to arrive and then retransmit the message, which is essentially a stateless communication protocol, which allows them to handle very highly dynamic conditions. So the protocol continues and spreads through the network like a wave or multiple waves, and eventually can be received by all nodes with a very high probability. Moreover, due to the way the protocol works, the nodes still may lose a packet, but these packet losses are highly decorrelated. It's sort of a little bit detailed to explain exactly why that is, but just to give you a high level idea, just look at this red node with the arrow. This node has at the beginning of the communication process, one chance to receive the message from its direct neighbor in blue. And then on the right-hand side, you see the same red node at a later stage during the communication process, and it has a second chance to receive the packet, this time at a later point in time, where the wireless channel conditions might have been or may have been more favorable in case it has lost the message at the first attempt. So it has a second chance at a later moment in time and from a different set of transmitters. So this creates a high diversity in the communication. Every possible path is sort of exploited by this scheme and therefore masks the burstiness of the individual communication links and therefore decorrelates packet receptions and losses. And we studied this both empirically and also more theoretically in the later paper here. Okay, so we have a very fast, reliable communication, and we have very favorable packet loss statistics. So now there's not only one agent in the system that wants to share its state. Of course, we have multiple agents. They want to maybe want to coordinate their activities. And therefore, communication is organized into rounds. So over time, at a certain precisely scheduled moment, all nodes engage and they communicate in these orange rounds, communication rounds. And in each round, there's a sequence of communication slots, these data slots here. And each data slot serves to, or allows one agent to share its state or whatever other data it has with all other agents in the system. So every slot here is a one-to-all communication. And by having a sequence of these slots, we essentially have a many-to-all communication system where all nodes are precisely synchronized and operate according to the same global schedule. Right, so now we have, on the one side, we have sensing, actuation, control, and I just explained the wireless protocol, this time-triggered communication protocol. But in order to minimize the end-to-end jitter and delay, it makes a lot of sense to globally synchronize all these different tasks. So to basically align communication with computing, sensing and control. And therefore we have a certain approach, a scheduling framework that globally schedules all these tasks in the system. We can derive multiple schedules for different operating modes and switch between these different modes at runtime. And by doing this, we minimize the end-to-end jitter and delay, and this is shown here in the figure. We did measurements of the end-to-end delay. So from the sensor across the network through to the controller, and then again back to the actuator. And what we are plotting here is the end-to-end delay along this whole path. What you can see is that the jitter is very small. It's between roughly plus minus 20 microseconds. And also the theoretical maximum jitter that we can possibly see in the system for update intervals that are interesting for us, so here 100 milliseconds, is extremely small. It's between plus minus 50 microseconds. And considering the kinds of physical systems we are looking at, mechanical systems that are operating of tens of milliseconds, on the order of tens of milliseconds, one can sort of neglect this very small jitter in the control design. Yeah, and this is summarized here. So by designing the hardware and software components of the network in a certain way, we can minimize the end-to-end delay. We still have delay, but it's very small. There's a negligible jitter that can be ignored essentially by the control design. And we still have packet losses, but they can be considered IID. And now I will hand over to Sebastian.
Okay, thank you, Marco. So we'll now continue with the control design, because what Marco has explained is we have achieved now a quite favorable wireless embedded system, and we've moved away from the long delays to a minimal end-to-end delay, basically one time step. We can safely neglect the jitter because it's orders of magnitude smaller, and we have IID packet losses that will be beneficial for the control design, as we shall see. So of course, we still need to take care of the remaining challenges like the packet losses and the delay, and this is what we're going to do in the control design, the control analysis. So we aim to account for the resulting or for the remaining challenges in the control design. So for this, we first of all develop or state a model that incorporates all the properties of also the wireless embedded system. And first of all, what is favorable for us now in terms of modeling is that we have this synchronized system. Like there's the synchronous communication, and therefore synchronous, all agents are synchronous in the entire network. And that means that we can basically now develop and use a discrete time model that captures the behavior of the entire system. So basically, as the discrete time step, we're going to now choose pretty much the communication round of the synchronous transmission. And then we know from what Marco basically explained is that now when we, for instance, communicate from the sensor to the controller across the wireless multi-hop network, that we basically incur one time step delay. So there's no longer a variable delay, but there's one time step delay, and same on the way back. So this means that we use a discrete time model of that sort. So we have basically for the physical dynamics, we assume LTI dynamics. We have some process and measurement noise, and then we assume here that we will measure the state or a noisy version of the state, and then there can be there's one time step delay basically on both paths. So basically the synchronous transmissions we capture in our discrete time model. And then, of course, there's message losses, and these we model as Bernoulli random variables. So we have one random variable here that basically captures, do we lose the sensor packet, and another variable here that says, do we lose the control packet? And what is now very beneficial is that we have a very straightforward, a very simple model of the packet loss. Pretty much it's a Bernoulli random variable, and these are independent, as Marco was pointing out. And this is very crucial here, because in many works on network control, you see this assumption actually of Bernoulli random variables, but often it's an assumption that may or may not be verified in practice. Here, we're basically building that assumption on top of the hardware design, as Marco was explaining. So this is basically our model then. So we have here, for instance, for the input here, we're going to say that this random variable here, it's 1 if we receive the packet. So then we basically use the input that that was computed at the controller in the previous time step. Or if we lose the packet, then we just implement a 0 order hold here. Basically, if we don't get new data, we just apply the control input that we had before. And then the controller design is basically a straightforward design where we pretty much use just the system dynamics to propagate forward to compensate for the delay, and also take into account the possibility of losing packets. So what we basically do here is we propagate the system dynamics here. This would be the actual measurement in case we receive it. In case we don't receive it, we use the previous state and propagate this forward using the A matrix, and then of course also the input that goes in here. So basically we're predicting forward one time step. And we do that as well also for the input, because we already anticipate over here that we're going to need one time step delay. So we also propagate predict this one time step further and then apply our feedback gain. So what we have here is a relatively straightforward system model and a straightforward controller design. And the reason why we can have such a relatively straightforward model is that we're building on the system design, the embedded wireless system design that actually has these properties. Now, if we take all of this together, we obtain a model that looks like this. So basically, what we have here, we've augmented the state with the input, and then also the copies of the state and the input, because there may be a discrepancy between receiver and sender side. And then this matrix here becomes time varying, and in particular, the time variability comes from the random variables. So these are the Bernoulli random variables that basically tell us, do we receive a packet or not? Now, that model basically now captures all the properties of our system. It incorporates the delay of one time step, essentially. We have jitter that we could neglect, and we have the IID packet losses. And now with this model, and the corresponding controller, which pretty much just uses the model to make predictions, we can now analyze the stability. And now, of course, it's beneficial that this is a relatively straightforward model that we're looking at, and this is the case without noise. So we also have the case where we have some process or measurement noise here, which we're not discussing here for simplicity, but it goes in a similar way. Now, what we have here is this matrix here, is the stochastic matrix. So depending on what the value of the random variable, this will change. And because it's a stochastic process, what we aim for here, or the stability definition that we're looking at here, is we're looking at the second moment and aim for this in expectation going to zero. This is the case where we have no process noise, measurement noise. With process and measurement noise, there's a similar way you can do this, but then you would aim for this not being zero but being bounded. And because of this system description, we can now basically leverage standard tools from control. So standard tools from LMI-based analysis here that basically looks at a system like this, where this part here is a stochastic probabilistic matrix. And we can use standard results like this one here, where basically we write the matrix in this form here. So now the PIs, these are the random variables. And then we have these matrices here which multiply the random variables. And even though our random variables are not exactly of this form, we can do a straightforward transformation to make them zero mean and then compute the corresponding variance. So we can bring our system here into this form. And then there are standard results that basically tell us that if we can solve the corresponding LMI problem, like this one here, we can solve it and find the matrix P. Well, then we know that our system is stable. And I'm sparing you the details of this, but it's basically what we need to do is just to transform this matrix here into this form, and then we can use standard tools. So the key here really is not so much that this is a new stability proof or something, but because of the co-design between the embedded wireless system and then the way we do the control, we could get this into a form where we can leverage basically existing analysis results from control. So it works in theory. So let's see if it also works in practice. So we wanted to, we'll build a testbed to evaluate and test our solution. And this is the testbed that we built. So it consists of 20 nodes. These are the nodes that we're using. These are the wireless nodes. So this is the dual processor platform that Marco mentioned with the application and the communication processor. As you can see here, this was developed together with Lothar Thiele's group at ETH. And this is a floor plan of the Max Planck Institute in Tübingen. That's where my group was at the time. And we've equipped this floor basically with 20 of these wireless nodes. And otherwise, it's just a regular office building with concrete, glass walls in between, other wireless equipment, etc. Just a regular office building. And then to test now whether we can use the communication for feedback control, what we do is we connect two of these with some inverted pendulums. So each of these has an inverted pendulum, and now we can do different tests. So for instance, we can test remote stabilization. So in this demo, what we're doing here is we have this node here attached to one of the pendulums. It measures the data, it measures the sensor data, then it sends the data over the network to some control nodes, for example, to this control node. So this control node receives the sensor data, computes the control, and then sends the data back across the multi-hop network. And similarly, for this pendulum here, it's sensor data travels through the network to here and then travels back. So we did this test to basically show and evaluate, can we reliably stabilize or do remote stabilization over this multi-hop wireless network? And indeed, we can do this. So this is some experimental data. So in black is the pendulum angle of the two pendulums, and red is the control input. And we can see the pendulum angle safely stays within ±2 degrees, for instance. And because of the way we have, the communication system set up, we can also freely move around nodes. And this is what we're showing here. So this is pretty much the experiment that I showed before, except that now we're not just using two nodes for control, but just one node that computes control for both pendulums. And now A and B are the pendulums. So you see in the top left, one of these pendulums moving around, and on the bottom left, this is one of the controllers. This is controller 18, and we're now taking this controller and moving around in the office building without changing anything. And as you can see, basically the pendulum just continues to stabilize without any problem. And this is a major challenge for other multi-hop networks, because these might have to reconfigure if the nodes are in a different position. And we don't need to do this because of the design of the wireless embedded system here. And then, of course, you can do more tests. So this is an experiment where we then basically looked at, okay, how does the performance change if we change the update intervals, basically to see like what's the trade-off between communication and control. And this is as expected. So if you increase the update interval, of course, you pay a price in terms of control performance. So this shows that basically the pole angle on average, it becomes a little bit larger. Of course, going to higher update intervals, this reduces the duty cycle, so you can save some energy as one would expect. And this, what we've shown here, was an experiment basically in the lab in our office building in Tübingen at the time. But we've also taken our experiment out to the outside, to a conference. So this was at the CPS IoT Week in 2019 back in Montreal in Canada. So this was a big conference. It's the biggest CPS conference, and we took our equipment and went there and basically set up our experiment in this big hall that you see over here. So this was a demo that ran for one night basically, and you can see here our setup. So we have these pendulums. We have two pendulums over here, and there's another pendulum you don't see here. It's in the very back over here. And if you look closely, we have a wireless node here. There's another one here. So there's a couple of wireless nodes that we've distributed over the entire hall. And of course, there were many people around, had their mobile phones, other wireless equipment, etc., etc. So this was a great, basically, test case for our solution. And what was great is that through the entire demo of several hours, we didn't have a single failure. So basically, we could do remote stabilization across this entire hall without, having a single failure in our system. The only reason that our pendulum would fall down was when we basically demonstrated, we unplugged the control node to demonstrate to the visitors that we were not cheating and we were actually doing remote stabilization. And this was great for us because obviously we had good confidence that our system would work, but that we didn't have a single failure over several hours was also a big surprise to us. Okay, so what I've talked about now is, or what I've shown you so far, is basically remote stabilization. But what about distributed control? So can you also do coordination of multiple control loops? And now here, of course, it comes very beneficial that the communication system basically allows for many-to-all communication. Or in other words, that if a packet is sent out, then basically by the design of the communication system, this packet will be received with very high probability by all the nodes. And this is, of course, very beneficial when you now want to do coordination or distribute control, because pretty much by design of the communication system, the data is available on all the agents. So this means you can now basically do a centralized control design, but implement the centralized controller in a distributed fashion. And this is what we're visualizing here or showing here. So here we have, as an example, task synchronization. So we now have multiple physical processes, and here we assume that we have some local controller. So here, for instance, for our pendulums, this will just stabilize the pendulum. But what we want to do now is we want to synchronize. So we want to exchange data over the network so that the pendulums, let's say, move in concert or are synchronized. Of course, because we have full information available at every node, we can pretty much just do a centralized design. And what we've done here is just a straightforward linear quadratic regulator design, where in addition to having the objectives of state and control costs for the individual agents, we also have this cost term here that synchronizes the motion between the systems. And then if you just do the math, you get to this formulation. So this pretty much is the standard LQR formulation, where you have now some off-diagonal terms here that account for the objective of you wanting the systems to be synchronized. And we've used this design on our system, where we basically have now again these multiple pendulums. And what we want to do now, in addition to balancing, so they do the local balancing, the local stabilization. Now we want the card positions to be synchronized. And what we do as well, like we have these two real pendulums and we have multiple simulated pendulums, just to increase the number of let's say, physical systems that we have. And this is experimental data. So this is, first of all, where we do not do the synchronization yet, where one pendulum is in blue, the other one is in orange, and these dashed lines here, these are the simulated pendulums. So the simulated pendulums are without noise, so they are just perfectly at zero. And the other two pendulums, they are moving around, obviously not synchronized here. And now we can just turn on the synchronization because the data is available on all the agents basically automatically, and then we get the synchronization behavior where now the pendulum positions are moving in sync. Okay, so with this, what we've basically achieved is we could basically fill this spot here where we have achieved fast feedback control over wireless networks, fast in the order of tens of milliseconds, but over a multi-hop network, so with large diameters, and all of that on low power hardware. Now, that brings me to the second part of this talk, where we want to talk a little bit more about resource saving. So what else can we do now? So we did here so far the focus was on periodic control and stability guarantees. Now we want to look at a little bit like can we save resources? And what we've seen in the previous experiments is that, of course, what I can do, and if I can allow for that from given the dynamics, reduce the synchronous transmission rate, and this way save energy. But of course, that's not the ultimate thing you would want to do, but you want to be a little bit smarter about this and basically ask like when do I actually need to send data and when do I not? So this is essentially the idea of what has been called event triggered control, where you ask at every point in time, do I now need to close the feedback loop or do I not? So before I tell you a little bit about what we've done, let me motivate what is the core idea of event-triggered control, and then also tell you what is, in our opinion, a key shortcoming of event-triggered control that we were then addressing. So this is the classic control, the classic periodic control, first of all, here on the left. So here what we have is we have a dynamical system and we have a control, and here we assume that the sensor link as well as the actuator link is closed over a network. And with classical methods, what we would do is we would do periodic sampling. So at equidistant points in time, we would sample our system, send it to the controller computes a command and sends it back. So this means at every point in time, we would need the resource communication. And now the idea of event-triggered control, just in general, is to introduce such event triggers here. Event triggers here on the sensor side that would decide, do I now need to communicate the sensor measurement or not, as well as here on the controller side. So for instance, if the control system is doing fine, it's roughly at steady state, you may not actually need to send a new control command because everything is fine. But then let's say there's a disturbance and that you want to detect, and then you want to send a new control command to do the control. This is the core idea of event-triggered control. And there's numerous schemes and algorithms that have been proposed that pretty much all fall in this category. So then the goal of event-triggered control is to reduce samples. So to get to sample patterns like this, so it's no longer periodic, there's some irregular sampling pattern where you say, okay, here I need a sample, here I don't, etc. So the goal really being kind of reducing samples in order to reduce resource usage. But this is now the core question. Does reduction of samples actually mean reduction of resources? And for this, let's have a little bit of a closer look at a typical event trigger. So this would be a typical event trigger here on the sensor side. So there's many variants, but they are all pretty similar in one respect. And a core aspect here in this triggering rule is that we decide to communicate this yk, so the y at time k, based on this property here, which also depends on yk. So the goal that often in event-triggered control, you're looking at the current data, at the current time step to decide whether you now need or want to communicate that data. And what does that mean? If we now think about the resources that we need to reserve for this, well, it actually means, because we're doing instantaneous decisions, you still need to reserve the resource, right? So in order for the agent to be able to communicate the data in case it needs, the communication system needs to reserve a time slot. Simply because we're making instantaneous communication decisions. So this means because we're instantaneous, we're actually not freeing up resources. And there's an analogy, like this is like back in the old days before the Corona pandemic, where stadiums were still full, and imagine that you wanted to, you got a ticket for the sports event of the year, and you want to go. So this is really like a scarce resource to have, you have that ticket, and then in the last minute you decide that you don't want to go, and that means you have this empty seat here, and because you decided last minute, nobody will actually benefit. So this means that basically this resource in that sense is wasted because nobody can use it. If you had decided earlier, if you had decided 1 or 2 days earlier, you could have given the ticket to someone else. And this is exactly the analogy to what I was saying about event-triggered control. If we make instantaneous decisions, we cannot use the resources in another way. And in that sense, it would be even more wasteful because the resource was reserved and you cannot actually use it. So this shortcoming, this is what we are addressing in this work. So what we are aiming at is that we want to realize now the benefits of basically the event-triggered sampling by better reallocating resources. And what we need for this is essentially 2 ingredients. On the one hand, we need predictive triggering, so we can no longer make instantaneous decisions. We need to anticipate whether or not we need to communicate. And then we need to integrate that with the communication system at runtime. And together with Marco, we have basically developed two approaches. One approach is self-triggered control, where pretty much the idea is that at the time when you send a packet, you already decide when you want to trigger next. And then you include this next trigger in the packet, and then the communication system can use this data to reallocate resources. The downside of self-triggered is, of course, like once you've decided when you want to communicate, you can no longer change that decision. So therefore, we've also looked into what we call predictive triggering, where we predict the need for communication some H steps ahead of time, and then we signal this to the communication system so that the communication system can deal with this. And this is what we want to focus on now a little bit for the last, let's say, 5 or 10 minutes to tell you how we focused, how we addressed this. So the problem that we're looking at here is, again, the synchronization. So we use the network to exchange messages to coordinate control loops. And what we assume is that we have M messages available, so the communication bandwidth is M messages per time step. And then we assume that this is a general purpose network where you have multiple sorts of traffic going around. And we assume that we have MA messages reserved for some other application traffic, and then we have MC messages for control. But the challenge now is that we have more agents then we have messages available for the control communication. And our goal now is that we want to determine online, and we want to find out online which are the MC agents that have the highest need for communication, and then allocate the messages to exactly these agents. This is the overall scheme that we've come up with, the overall predictive triggering scheme that we use, and we're going to say a few things on the control system, and then Marco will say more on the communication system. So on the control system, we use a pretty standard architecture of event-based control and estimation, where we have locally here we assume that we have the state measurements. We could also do state estimation, but here we assume that we have state measurements. And then we also locally estimate kind of the state of the other agents. And then these two fuse into a controller that we then use to control the local agent. So basically here you have both the local state as well as predictions of the other state. And now the challenge, of course, is that we have N agents, but not enough communication messages. So not every agent can just send their data here through the network. And for this reason, we need to come up with a priority measure. And here I'm just giving you the very brief idea. So how do we do this? How do we get this priority measure? So what the core signal that we're looking at now is, of course, the difference between the prediction of a state and the actual state. And basically, when this error becomes too large, that's when we want to communicate. Because on the contrary, like if the prediction is doing fine, if the prediction is close to reality, then there's no need to communicate. And in this work, what we're looking at is we're looking at this norm. So it's basically the squared Mahalanobis distance that basically measures the expected value of the error squared and scaled with the inverse of the variance. And then we define the priority measure as this one here, where we now look at this norm, but importantly, predicted H steps ahead of time. So we're going to say we take H time, predict H times into the future whether we need to communicate or not. The idea is that if this becomes larger than delta H times in future, then we will want to communicate. Or this is what we use as a priority measure. And if we use a conservative estimate, then we can compute this in closed form, at least approximately. And when we have this priority measure, we basically get this scheduling demand. So we're going to say that we would like to schedule our agent in at time k plus h to communicate if our priority here belongs to the MC largest priority. So PMC here is those priorities, the MC priorities that are the largest. So obviously, if one of that means if our agent is one of those, one of the MC that has the largest priority, we want to communicate. And in addition, we include these constraints here as well that basically say that if the priority is lower than some kind of small priority, so basically there is a priority, but it's very small, then we don't need to communicate. So this basically means that if all have low priority, we don't need to communicate. And then what we also look at is that at the time where we want to communicate, do we still need to communicate? Because things might have changed, that our priority has decreased, and therefore we may not need to communicate. And if these requirements are fulfilled, then we can give similar stability guarantees to the type of guarantees I was saying in the first part. And now with this, I will hand over again to Marco to basically tell you how we can now use these requirements, these online requirements for scheduling on the communication side.
Yeah, thank you, Sebastian. So how can we satisfy these requirements that are now coming from the control side? for this, we have to design a scheduling algorithm and cater for an efficient and reliable exchange of these priority measures from among all the agents, and of course exchanging also the state of the agents if an agent is scheduled to do so. So let's briefly look at the scheduling side of things. So we were here having an online scheduler. So compared to the first part of the talk where everything was sort of scheduled in advance, now communication decisions are being taken at runtime. And this also happens in a different distributed way. Every agent runs exactly the same online scheduler, and the input to the scheduler are the priorities from all the agents that have been received at time step K. And the output of the scheduler is which agent gets to transmit in the next communication round. And an agent I gets to transmit its state in the next round if and only if it has actually received all the priorities. So this is a safety measure. If an agent has not received all priorities, then it may compute a different schedule compared to the other agents in the system, which would lead to an unreliable communication scheme. So therefore, an agent needs to receive all priorities to ensure schedule consistency. Luckily, this happens with very high probability given the properties of our communication scheme. Then there are these two other conditions that Sebastian already mentioned. So agent I's priority needs to be among the MC highest priorities and exceed this user-defined threshold. So that's sort of the predictive trigger that allows the system to arbitrate, to reallocate resources based on the need to communicate. And finally, as Sebastian also mentioned, there's this instantaneous trigger. So agent I will wait until shortly before it is bound to transmit and check again, am I still exceeding this user-defined threshold? And if it has a lower error or a lower need and does not exceed this threshold, it will back off and allow the communication system to save resources. Reallocation is not possible in this case because it's just not enough time, but still we can save resources. And this is just a very high level idea of how the communication system works. So now communication in orange here over time is intertwined with scheduling, where the scheduler runs to compute which agent is allowed to transmit in the next communication phase. And as you can see, or as try to illustrate, the communication resources are adaptive. They may change over time based on the needs of the agent. And the communication scheme is, from a high level perspective, similar to what we have seen in the first part. It's a globally time-triggered communication scheme. But under the hood, we use in-network aggregation and network coding to make this exchange of the priorities and states even more efficient and also reliable, and very efficiently aggregate the priorities from all the agents. So this is illustrated on the right side. So this is basically a packet. It's a message, and the black part of the message, these are the priorities. And over time, from top to bottom, you can sort of illustrate it that over time, agents are sort of accumulating or aggregating the priorities from all the agents in the system. This is being embedded in the packet and then shared again. And on the right side in blue, yellow, and red, you see that we are using kind of network coding to make this a little bit more efficient. So I don't have time to go into more details, but ultimately what we're having here is a way to sort of very quickly adjust to the communication needs as determined by the scheduler. And this is enabled by exchanging the priorities among all the agents. So this is an all-to-all communication, and still having many-to-all exchange of the states of the agents. Right. Okay, so that concludes the design part. And in addition to theoretical analysis, we also performed experiments here for this type of system where the goal was to save resources. We have, again, our 20 agents, but now every agent is co-located with a physical system. We have 6 real physical systems, so real pendulums, and 14 simulated inverted pendulums. And again, we are looking at this synchronization of the card positions while each agent locally stabilizes the pendulum. And halfway through the experiment, we sort of fixed, so we sort of injected a disturbance at one of the agents by fixing the card position at location 20 centimeters which is in contrast to the goal of the stabilization, which should happen around position 0 centimeters. And what is shown here in the plot is the number of messages that are being allocated to the different agents by the communication system, or by the scheduler and then by the communication system. And as you can see, all the simulated agents in gray, for example, 1, 4, 9, 10, and so on, they are not allocated any messages because there's no noise in these systems. They are perfectly predictable and don't have any need to communicate before the disturbance. And only the real pendulums or agents with real pendulums need to exchange messages. After the disturbance, as you can see, agent 11 suddenly has a very high need. It needs to announce, hello, I'm disturbed. My card is fixed at 20, and it's being continuously allocated messages to share this information with the other agents in the system. So that sort of illustrates that the system correctly schedules and transmits messages based on the actual need to communicate. And this is determined at runtime, with and without disturbance. Right, so let's move on to some concluding remarks. And Sebastian, maybe you want to start.
Yeah, thanks, Marco. So basically, when Marco and I were from separate communities when we started collaborating. So even though Marco and I both did our PhDs in Zurich, we didn't actually know each other until I had left Zurich. And I mean, I was working in controls, doing event-based control, but for wired networks, and Marco was working in wireless communication for sensor networks. And then we got together because I was interested whether I can use my algorithms on wireless communication. Marco was interested, among others, whether could also do feedback control with his system. And so we got together, and from this collaboration, I would say in retrospect, the main contributions of what we achieved is basically really the integration of communication and control. So as in the first part, for instance, I was explaining that the tools from, like, let's say, for the stability analysis or stability design were already there. But what we did is we combined them in new ways, and basically by integrating the embedded communication system with the control system in such a way that we can then use the tools that are available in control, really made the difference here, that we could achieve things that were not possible before. And then, so really it's the integration of the two that is, I would say, the main contribution. But then, of course, from that integration, there were also, contributions on the individual side. So it became apparent that just doing event triggering and instantaneously doesn't make sense from the communication side of view, because you need to be able to anticipate. And that's then basically gave rise to asking the question about predictive triggering. Or on the other hand, when we said we have the predictive trigger, we needed an adaptive scheduler on the communication side. So that then led to basically two contributions also on in the individual disciplines. And what we understood is that there's really different types of integration on different levels. So there's the integration of control and communication at design time, but then also at runtime. And from my point of view, especially from event-triggered control, which was very interesting, is that when we looked at kind of a lot of the research that was done in the last, let's say, 2 decades or so in event-triggered control, which was a lot, then almost all these works are motivated by, okay, let's make better use of the available resources. But the point is, as I was saying before, is that if you don't integrate that with the communication system, you cannot actually use the resources in a better way. Like the analogy with the empty seat in the stadium, like if nobody is using that resource, well, then it's really a waste of resource. And it's only with the integration of communication that we could then basically show how we can actually get these event-triggered control algorithms to make better use of the available resources. And that was, in my view, an important insight from this that emerged only from this collaboration.
Right, and to realize these resource savings, it became apparent to us that we have to have a very highly adaptive scheduling and communication system, and this really pushed us to the boundaries. And now it's even possible now to react to instantaneous trigger decisions to at least save resources. We cannot reallocate, but drove us to design a communication system that can save resources using instantaneous event triggering decisions, while arbitrating based on the predictive information that we get from the control side. Moreover, I think one of the key messages from our side was that we sort of focused more on guarantees and predictability, and that also packet loss statistics are really important for a very effective integration with the control side at design and runtime, rather than only pushing performance, which is what you see in many other wireless communication communities. There are terms like ultra-reliable, low-latency communication, where people working in isolation on the communication side assume that it's always better to have, basically no packet losses, or I don't know, 5 nines reliability and extremely small latencies. But what we saw is that it's actually much better to look at the tail latencies and trying to bound latencies, achieve real-time properties, and also, as Sebastian explained, for this stability analysis, the decorrelated packet losses were really important. So it's a different kind of focus compared to other works on the communication side. So in summary, I guess all these contributions were only possible by having an intense discussion and collaborating, trying to understand each other, which was not that easy in the beginning, even though the fields are pretty close to each other. It took some time. But this has been highly beneficial, leading to novel scientific results, couple of awards for some of the works, and demonstrations on real hardware that show that we can actually translate results from theory into practical systems. So I guess with that, I would like to conclude this long talk, and I guess we're happy to take questions if you have any.
Thank you very much, Marco. Thanks a lot, Sebastian, for the great presentation.